Hello, class. What we're going to discuss now is nomenclature of alkanes, excuse me, called bicycloalkanes. Now, we've previously seen alkanes in a ring structure like that, so that would be cyclohexane. But the moment that we stick another ring on it, okay, so let's say if I added that to it. That right there is called a bicyclo compound or a bicycloalkane. And the reason why is because now this ring has two rings. So what we could see here is you could see in blue right here, that six-membered ring right there. Okay. But then what's on the inside? Looks like a five-membered ring, right? And so what we have going on here is we need to be able to draw these molecules, okay? And so you could, so let's just go back and do something simple. Okay. Let's see here. We could just look at cyclohexane, okay? And we could take that molecule and draw it like this. So just draw a little, like a little bit more broader. Boom, boom, and then in like that. All right. So that and that represent the same thing. And the reason why we draw it like this is because when we add that extra carbon right there, so there's a total of 7 carbons in this molecule. We can represent it like this. We can number that number 1, 2, 3, 4, 5, 6. Now this is just for numbering purposes, just so you can see where everything is, okay? This numbering process that I'm doing right now is not for nomenclature, okay? So we see carbon 4 has a carbon that's bonded to carbon 1, like that. Do you see how I put a little gap? So this bond right here, do you see how I put a gap right there? Why is that so important? Is because if, let's draw it where I didn't. Let's draw it like this, okay? What's the difference between this molecule here and this molecule here? Well, this molecule here has 7 carbons. This molecule here has 8. Why? Because every junction is a carbon. So 1, 2, 3, 4, 5, 6, 7, 8. But here you can see 1, 2, 3, 4, 5, 6, 7. That's all there is. So when you draw the rings like this, when you draw this little triangle right there, you have to put a little gap in between it there. Okay. So now what we have here is we have the molecule looking like this. All right, so getting rid of these numbers here. So this is that, representing the same thing. Now let's talk about this bicycloalkane. What's the name of this? Well, it has 7 carbons, right? So we can call it a bicycloheptane, like that. And in a bicycloheptane, we have what's called bridgehead carbons. All right. Bridgehead carbons, like so. And the bridgehead carbons is that carbon there and that carbon there. And we will get to it momentarily. How do I know those are bridgehead carbons? Okay. So we'll get there in a second. But we have, when you look at a compound, it looks a little funky with 2 rings. We call it, 2 or more rings, we call it a bicycloheptane. So the bridgehead carbons are the carbons that join the 2 rings together. So if we look at it in this structure right here, I could view it this way. I could see a ring like this. There's 1 ring right there. And then I could also see this, I can see the second ring right there. So I have that pink ring and that blue ring, and where are they joining together? They're joining together right there. And so that's what we see in this structure right here. This is our bridged head carbons right there. Now, why is this important to find the bridgehead carbons is because when you take a look at another molecule, okay, what if I draw another molecule that looks like this? What's the difference between this guy and this guy? Well, when I look at it, this is a bicyclo alkane, and it has 7 carbons. So I could call it bicycloheptane. But when you look at the 2 structures, you can clearly see that they look different. But how can I name them the same thing? If I did, which one would you know I'm talking about? So that's the thing that's that's why the bridgehead carbon is so important, is because now it's going to help us figure out how to actually name it more specifically so I know exactly which one I'm talking about. So if I look at this one on the left, the bridge carbons would be this guy right there and that guy right there, because those are the carbons that are joining the 2 rings together. Now, when we take these molecules, we are going to now use nomenclature to figure out what the name is. Okay? So when we let's look at this one here. What you're going to do is you're going to identify the 2 bridgehead carbons, and then you're going to try to find the longest path that's connecting them. Okay? And so you can start here, and I can see I could go 1, 2, 3. Okay? So that's a path. Boom, boom, boom. Okay? Now within that path that's connecting the 2 bridge carbons, we count how many carbons there are in between those 2 bridge carbons. So we count 1, 2. There's 2 carbons in between this path. So I make that note, mental note, okay, that there's 2 carbons in that longest path. Now, what if I count the other way? There's going to be 1, 2, 3, okay? There's that path. You see that? Now, how many carbons are in between the 2 bridged carbons? There's 1, 2. So there's another 2. Now I find another path between the bridge carbons from this path to that path. And I see 1, 2. How many carbon atoms are in between those 2 bridge carbons? 1. So this path right here. So 1, and then I put a little like that. And so these numbers right here are going to tell us the name of the compound. And so the way we actually name it is bicyclo, and then we use brackets, and then we put in the order the longest paths. So 2.2.1 bicycloheptane, like that. So how would we name this guy? Well, we've identified the bridgehead carbons, and so we find the paths. So let's go starting here. 1, 2, 3, 4. So you don't count the bridgehead carbons. So from there to there, I followed this path. So we have a 1, 2, 3, 4. No, sorry, we don't. From bridgehead to bridgehead, it's 4 carbons. 1, 2, 3, 4, 5. But we only count what's in between. So 1, 2, 3. So we have a 3. And then we could start here and go boom, boom. So that's 1. Or I could have went boom, boom. And that is also 1 carbon in between. So we would call this guy a bicyclo 3.1.1 heptane. So what's the difference between the two? It's the numbers inside those brackets. And those are what's going to show us these numbers right here is showing us the connectivity of these rings. That's the important part. Now let's take a look at a bicycloalkane that has substituents on it. And here we have 1 methyl substituent. So the way I like to name these molecules, I understand that we have a bicyclo. How many carbons are in the ring? And I count 1, 2, 3, 4, 5, 6, 7, 8. So that's a bicyclooctane. Now I know that's not the correct name because I don't have the numbering scheme for the bridgehead carbons, right? So then I need to identify the bridgehead carbons. I see that they're there. Okay. Now, typically when you name a alkane, you always want to give your substituents the lowest locant number, and that's typically how you do it, but not with bicycloalkanes. What you do is you first figure out what numbers go into those parentheses. All right. And so let's do it here. So we got to find the paths here. So we have something, let's do this one. From this bridgehead carbon to there, what do we have? 1, 2 carbons in between the 2 bridgeheads, so 2. But do I have a path that's longer than 2? Well, what if we went this way? That is 1, 2, 3 carbons in between. And we always just we rank them from largest to smallest. And then we see from this, we can follow this path right there, and there's only 1 carbon, so 3.1. Now we have to kind of memorize this 3, 2, 1 because we're going to follow that path in order to prioritize the locant numbers. So it's telling me to go through this 3 path. So I could start right here. Number that carbon 1, 2, 3, 4, 5. Do you see how this number right here is telling me to follow that path? Once I stop at a bridgehead carbon, I look at the next number, and that says 2. So follow the 2 path. So I'm going to go 6, 7. So I'm following this path back to the bridgehead carbon. There's my 2. Boom, boom, boom. And then it says, now I stopped at this bridgehead carbon. Now follow that path. So right there. So that would be carbon 8. Do you see how I'm doing the numbering scheme by following the path here? I'll do another example to hopefully make this make more sense. So now that I have those numbers here, I see that my methyl group here is on carbon 8. So we can name it. Let's see here. So that would be, do I have enough space here? Let's write it here. That would be 8-methyl right there. Bicyclo. Now we have to do the parentheses. 3.2.1, close parentheses, and then it would be what? 8 carbons, so octane. And I'm going to run out of board space. And you see that I ran out of space, but that's going to say octane. So 8-methyl bicyclo 3.2.1 octane. Now with this one, we see it's a bicycloalkane. We count how many carbons are in the ring. Let's start with this one. 1, 2, 3, 4, 5, 6, 7, 8. So it's another bicyclooctane. Now we have to figure out the paths here. And so we identify that and that as our bridgehead carbon. So let's look at the path. There's 1, 2, 3. We get back there. So there's 3 carbons in between. And it's not commas, it's period. Then we can go 1, 2, right there. So that's a 2, and then 1. Okay. So there's our paths. Now we have to select here a correct path. Okay, so let's do this in colors here. What if I numbered it this way, following 3, 2, 1? So 1, 2, 3, 4, 5, 6, 7. Come back here, then that's 8. Like that, okay? That's one path. What if, why could I have not have done it this way? Why could I not have started here on this bridgehead carbon? 1, 2, 3, 4, 5, 6, 7, 8. Because when I looked at the path in blue, I did 3, 2, 1, 3, 2, 1. I followed that. But I can also follow that in the pink way as well. Watch. That's the third pathway, second pathway, the last pathway. So now we have the blue numbers and the pink numbers. Which ones would you choose? Well, we want to give the substituent the lowest number if we have a tie with numbering the bicyclo ring. Now, when we're numbering the bicyclo ring, we have to follow this path. But if there's 2 ways to go about this path, then you give the substituent the lowest locant number. So that would be the 6, or the pink numbers. So the name of this compound is going to be 6-methyl bicyclo 3.2.1 octane. All right. So that's the nomenclatures for bicyclo compounds. Okay. Now we're going to shift our focus on what's called constitutional isomers of alkanes. Now we can have formulas for alkanes, okay? And I could take that formula right there and draw that molecule. There's 1, 2, 3, 4 carbons, and then there's 10 hydrogens. But then what is a constitutional isomer then? Well, I can draw another molecule with the same amount of carbons and hydrogens. What if I drew it like this? Do I have the same amount of carbons? Let's count. 1, 2, 3, 4. So 4 carbons. How many hydrogens do I have on this molecule? 3, 6, 9, 10. So this molecule and that molecule, you can clearly see that they look different, right? They are different molecules. They have different names. They look different, but what do they have in common? The exact same chemical formula. And that is what a constitutional isomer is. The same molecular formula, but different connectivity of atoms. They look different. You can see that we have a zigzag like this. That's the connectivity. But then the zigzag looks a little different on this guy. So if we take a pentane, what could be one of the structures? Well, just draw a zigzag. 1, 2, 3, 4, 5. There's 5 carbons, and there are 12 hydrogens. But could we figure out a constitutional isomer for this? Well, what if I just took this carbon right here, chopped it off, and put it over here, like this? Just stuck it right there. Do I have 5 carbons and 12 hydrogens for this molecule? 1, 2, 3, 4, 5 carbons. And there's 3, 6, 7, 8, 9, 10, 11, 12. So that is a constitutional isomer. Could I draw another one? What if I did this? 1, 2, 3, 4, 5. So that's 5 carbons. And then we have 12 hydrogens. So they have 3 constitutional isomers here. Now look at this. If we go to C6H14, you know how many constitutional isomers we have of that? We have about 5 of them. Now look at how crazy this gets. If we have 7 carbons, we're going to have 9 of them. Now I'm just going to skip down to 10. Look at this. 10 carbons. So what's that? 22. I'm just double checking the numbers here. Look how many constitutional isomers there are. 75. And the number just gets exponentially larger and larger and larger as we increase the amount of carbons. So you may be thinking, how do I know how to draw all the isomers? There's no trick to it. There's no strategy really. You just start doing your zigzags, making sure you have enough carbons and enough hydrogens, and if it matches the chemical formula, then you've done it. You've made a constitutional isomer. Now the challenge that you're going to run into is when you do duplicates. Okay. So let me show you what I mean by duplicates. As you're going through all of these, trying to figure out all the isomers, you'd be like, okay, here's our hexane. So we could do 2, 3, 4, 5, 6. Oh, that's a beautiful molecule. Okay, and then you take that most simple one and then you start moving the atoms around and trying to figure something out. Well, what if you came up with, let's see here, 1, 2, 3, 4, 5. What if you came up with an isomer like this? All right, so that's 1, 2, 3, 4, 5, 6. So that one's correct, or that one's valid. I'm going to erase this one for a minute. So you're like, yeah, that one looks good. And then what if you draw a molecule like this? And you're like, 1, 2, 3, 4, 5, 6. Perfect. And you look at these two molecules and you're like, based off of visual inspection, you're like, they're different. They look different. They're isomers of one another. Same chemical formula, but different connectivity. But oh, you got to be careful. Oh, you got to be careful. Why do you have to be careful? What's the common feature about a single bond? A single bond can rotate. Okay? They can rotate. And so what is actually happened here, these two molecules are not isomers of one another. They are identical. It's just the bonds have been twisted to make them look different. You can take this molecule right here and twist these bonds, and it will match perfectly with this one. So this molecule right here, if we call it A, is that molecule. And at the beginning, we called this guy B because we're like, A and B are different, but we got to be so careful because if we can twist and rotate around these bonds, we will see that A actually is B. So both of these molecules are the exact same. They are identical. They are not isomers of one another. Now, how can you figure that out? Well, you can rotate molecules in three-dimensional space. Okay? So let me just show you how I see it. And some people can see it very well and easily. So what I'm going to do is I'm going to take this molecule here and twist it 90 degrees. And when I twist it 90 degrees, so we'll go here. I'm going to twist it 90 degrees, okay? And it's going to look something more like that. Okay, let's put it more like that, okay? And then I'm going to take this bond right here and just rotate it. And then when I rotate it, I'll rotate this carbon right there down. I'll just rotate it down. This carbon here is still there. Now do you see this matches that perfectly? So they're identical. Now, one way to help get your brain to see this is to pull out your model kits and make these molecules. And put them together just like Legos and rotate the atoms. You'll see that the whole molecule can rotate. Now, for some people, that visual representation is just too difficult to see. Okay, and that's fine. So there's other ways that we can figure this out. If you're not a visual person, how can I tell that both of these molecules are identical? Okay. Use the IUPAC. Name the thing. Right? So let's name this guy So we find the longest carbon chain, 1, 2, 3, 4, 5. And we have a methyl group there on carbon 3. So that would be a 3-methyl pentane. That's how that's named, right? Okay. Now we come over here and find the longest carbon chain. 1, 2, 3, 4. That's not long. 1, 2, 3, 4, 5. Okay. So how do I number this? Do I number it from this direction? 1, 2, 3, 4, 5? No, because we want to give our substituent right here the lowest locant number. So that'd be 1, 2, 3. Wait, am I lying here? Let's double check. The locant number is at 1, 2, 3. Okay, and if I number it the other way, it's at 3. Oh, so it all works out the same. So what have we found? That we have a substituent at carbon 3. So that's a 3-methyl. And 5 carbons long is the longest carbon chain. So that's a pentane. And then I evaluate 3-methyl pentane, 3-methyl pentane. Boom. Exact same name, exact same molecule. They're not isomers of one another. So that's one way that you can double check yourselves if you're making any duplicates. All right? So in the energy industry, we use gasoline to fuel our vehicles. And we've all heard of octane because you have the octane numbers there on the gas station gas pumps. And so we have octane, and we take octane. Let's represent that by this. 2, 3, 4, 5, 6, 7, 8. So that's 8 carbons long. And if we add some oxygen, okay, and then we add a little spark to it, we're going to combust that, and that's going to turn into 8 moles of carbon dioxide plus 9 moles of water. Okay. Now, how much oxygen does it need to make this balanced here? It's going to need 12.5. Okay. 12.5 moles of oxygen to combust here. Okay. But what if we looked at an isomer of octane that looked like this? All right. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbons, 8 carbons. And if we treat that with 12.5 moles of oxygen, put a spark, that's going to combust into 8 moles of carbon dioxide plus 9 moles of water. Okay. So both of these give the same amount of carbon dioxide and water. But look at this difference right here. The heat of the reaction. How much heat or how much energy is given off when you take this molecule and burn it with oxygen? You get a number of 5,470 kilojoules per mole. Okay? You can't see the moles part there, but that's moles. Kilojoules per mole. But if you take this isomer, constitutional isomer of octane, it's going to give off a different amount of heat. 5,452. So this is quite interesting. Same amount of carbons, same amount of hydrogens, same amount of moles of everything, but one gives off more heat than the other. So it looks like this octane, the linear octane, gives off more heat, gives off more energy than a more compact molecule with the same amount of carbons here. So what this is telling us is the stability of the alkane, because this is releasing more heat when it combusts. And that's when we burn something, we call it combustion. So when this combusts, it gives off more heat. And the only reason why this gives off more heat is because it's more unstable. So maybe to make sense of that, let's draw a diagram here to illustrate that. Okay. So if I draw myself energy diagram here. Okay. Now what we have is our energy, the heat of combustion. Okay. That's just a not symbol there. So how much energy is given off here? Well, what's interesting is that when you combust the linear octane versus the compact octane, you generate the same product, and that is carbon dioxide plus water. It does not matter if you burn the linear octane or the compact octane, you get the same product. So if we have, let's draw it here in a different color now. Here's our linear one, 2, 3, 4, 5, 6, 7, 8. Okay, and we'll put its energy level right there. In order, when it combusts, it released a negative 5,470 kilojoules of energy. Kilojoules per mole. That's the energy gap between the starting material and the product. That energy gap. But what's so interesting is this number right here is smaller. And the only way that could be smaller is if the starting material is lower in energy. And so this energy gap right there is a negative 5,452 kilojoules per mole. And so what we're learning here is this molecule right here is more stable than the linear form. And so there's an area of research when we look at molecules. Do you remember from general chemistry doing calorimetry, where you were doing reactions in a calorimeter to measure the heat that's released or absorbed? And in this particular case, we use a calorimeter. We find out how much heat is given off when you burn these different types of fuels. And so from one perspective, you can do these calorimetry experiments to determine which molecules are more stable. So I think that's pretty slick.